Okay, all right. So we've just finished quiz 1. I'll grade that this afternoon and put the grades into MU Online. I also have some homework that I'll be grading this afternoon, so you should be getting some entries in the gradebook real soon. Your next assignment, homework 3, I've posted the PDF for that in MU Online, and you'll need to upload it by Tuesday, September 12th. So relatively quick turnaround on that assignment, but the good news is that you're going to be using StormCAD, which is always, like you can knock stuff out quickly and do lots of iteration fairly easily. And then for stormwater detention, that's essentially an Excel spreadsheet that you'll be using for that, the majority of it. And so we're going to use Excel a little bit today in class and show you how to size ponds. All right, so back to this example that we didn't quite finish last time. Let's open up the file. Hopefully you saved a file for the example we were working before. All right. Here's what we had. We had just a fairly limited network, and I think the last step that we had gone through in the demo in class last time was assigning the catchments to the inlets that they were going to be feeding. And so if we review, we've already defined these conduit slopes. It just is the default conduit diameters for now. Let's pull open the flex tables and take a look at what we've got defined. It knows the invert data for these inlets, and it's using the invert of the inlet as the beginning point of the pipe. We've got the standard pipe diameters here, just the default, and from the end value you can see it's concrete, and it's already calculating a capacity of the pipe based on Manning's equation. And ultimately what we want to do when we calculate the model is see the ratio of the flow that's going through the pipe relative to the capacity. And we want it to be as close to 100% but not over 100% as possible. And our design optimization is simply going to be changing these pipe diameters. All right. I want to show you one thing that might come up as you work on the assignment, and that is if you double-click on a single element, remember I mentioned in class last time that it assumes an upstream and a downstream direction depending on where you click. And so the first click you do is the upstream, then your second click is downstream. If you mess that up somehow, and you may be getting an error message that the water is flowing the wrong direction, here's this node reversal button. And so we can see that the starting node for us is 1.2 and the stop node is 2.1. So let's just make sure that that is accurate based on what we'd expect. So water's going from 1.2 to 2.1, and that's correct because I clicked here first and then I clicked on the other inlet. But if I had accidentally messed that up, all you need to do is click on the ellipsis here, and then it will reverse the start and the stop. So if I click on that, then now you can see the water's going from 2.1 to 1.2. So if I executed my model with it that way, I'm going to get a mistake. So I don't want that, so I'm going to switch it back. But I just wanted to point out to you that you don't have to start over drawing all of your elements from scratch if you have that reversal. You can just single click on an individual item and flip it. Okay, so we've drawn a network, catchments. The characteristics of the catchments are specified. Let's just make sure we've got C values for all of them. Yep, C values are here. Times of concentration that was taken from the handout that we had. These times of concentration would be something that you would calculate offline using one of the methods that were discussed earlier in the lecture that was recorded. We had already defined the storm data. Here under storm data is where I put in a user-defined storm, and I used this to add a duration of 5 minutes, 10 minutes, 15, and so on. One of the kind of cool features of the program under the storm data is you can, let's see here if we can get it to work, Hydro 35. You can just use a couple of parameters for the 2-year and the 100-year storm, and then it would extrapolate for all of the different return periods in between and different durations in between. So that's a nice feature if you wanted to analyze a network at lots of different return periods. But for our purposes, we're just going to be using this user-defined IDF table. So let me delete that Hydro 35. All right, so any questions about what's on the screen right now? All right, so what I want to do is go here to global storm events, and that's where you tell it which storm to use as the input storm for the simulation we're about to run. So in global storm events, my only option is the one storm that I've defined here. So it'll be available in the drop-down box that I called it a 5-year storm, the one that I created there. So I choose that as the input storm to run, and then I just click compute. And didn't get any error messages. That's good. It says that convergence was achieved. It only took a single iteration because this is a relatively simple network. So now I can double click on an individual element and it will tell me what is going to be the flow rate through that element. But the far more interesting way and efficient way to view this information is either through the flex table. So if you go to the conduit table, we can now look at that ratio over here of flow to design capacity. So all of the pipes are undersized except for this one that goes to the outlet that, remember, is just kind of ridiculously steep because it doesn't really exist. My assumption being that there's something downstream of this network stub that can accept all of the flow. So all of the real pipes that I actually kind of am trying to size, so pipe A, B, and C, those 3 pipes are too small because the flow is bigger than the capacity, 114%. So of those 3 pipes, of A, B, and C, C is the most badly undersized. You'll see 320%. So it would be the one that would fail first, pipe C. So to iterate, I can just change the size. So let's say in the homework assignment you have a variety of different pipe sizes to choose from. I specify that. Let's see here. Homework 3. So we've got 6, 8, 10, 12, 14, 16, 18. So here's all the pipe sizes I ask you to choose from among in designing the sizes that you need for this network. So I've got it set on 12. Let's try a 14, 16, or 18 if that's big enough. Okay, so let's make pipe C an 18 and A and B a 14. And then all we have to do is execute that model over again, and it will update the ratio of flow to design capacity. So it does the calculations, no error messages, that's good. So now we're getting awfully close, 108%. So both C and B need to be larger, but A doesn't need to be larger, and when it was smaller, when it was 12, it was too small. So pipe A is as good as we're going to get. We can't make it any smaller or any bigger. 14 is our best size there. But let's see, what was the next one beyond 18? What was it? 20? All right, so let's try 20 there, and we'll just run that one again to see. Okay, so now we're down to 82%. That's good. And we'll go from 14 to 16. Here on pipe B. All right, so now we've got an optimal network. The things are as close to 100% as we can get for the incremental pipe sizes that are available. So that's going to be the minimum cost. So what do you think we do next? Remember the parallels between this and WaterCAD. When you had a network like this in WaterCAD and You achieve convergence. Now it's just a matter of turning it in and displaying your work. What do you think you ought to do? Annotations. Annotations, like a map where the sizes are actually shown on the screen there, so that whoever is looking at your network doesn't have to open up some separate tabular file someplace. And so annotations are just the same approach. I'm not sure what's happening. The screen keeps changing there. Okay, so for annotations, these little weird, I'll try to get rid of that. Okay, so you'll right-click, New, Annotation. So for the conduits, maybe we would want to have it be the diameter. And then we would give it a prefix, D equals, let's see where that ends up. Okay, it's putting it right on the pipe, so we probably want to do like a location offset, maybe 2 and 2. Let's see where that moves it to. It seems like the sizing is pretty reasonable. We don't have to do a size multiplier, anything like that. Let's give it another vertical and horizontal offset, maybe 4. All right, so we've got the names, we've got the diameters. In the assignment description, that's not the right one. Okay, here I tell you that I'd like you to prepare 2 maps for what you submit. One of the maps is going to be focusing on the network itself. And so it should have like the element length, the diameter, the flow rate, and then the percent full that it is. And then the other map is going to focus on the characteristics of the catchments. And so you'll have the catchment name, the area, the runoff coefficient, and so on. So 2 maps, and I think I've asked you to submit those as PDF files to MU Online. So are you excited to use StormCAD? I can see the enthusiasm. I'm excited for you to use it. It's a great program. Simple. You can make a lot of progress really quick with it. All right. So we finished up that example. Now let's talk a little bit about the effects of urbanization on runoff. This top figure is something called a hydrograph. Let me write that on the board because it's different from a hydrograph. The one on the bottom is a hydrograph, which is basically just a visual representation of runoff. But a hydrograph is a visual representation of rainfall. And so the way to interpret this figure on the top is that they're measuring rainfall maybe in 15-minute increments. And for the first period, the rainfall intensity was some amount, and then the second 15-minute period, the rainfall intensity was higher, then it stepped down again. So what we're looking at on this top figure, the hydrograph, is we're looking at 3 different periods when there was a certain amount of rainfall intensity. And then the physical response to that rainfall intensity is the hydrograph that we have here. And so on the horizontal axis is time, the vertical axis is runoff, and then the 2 curves represent before urbanization and after. So there's 2 important characteristics that you have to keep in mind for what happens during urbanization. Urbanization is going to move the peak to the left, and it's going to make the peak higher. Okay, so why? Let's explain the why of both of those. Why does urbanization, taking raw land and turning it into buildings and roads and homes and pavement, why does it give you a higher peak runoff? Exactly, right. So there's not as much water being absorbed by the ground, and so then it has to go to runoff because the inevitably the development is going to make the surface more impervious. Now what about this shift in time? That maybe is less obvious. So what does that mean and why is it happening? The fact that the after urbanization hydrograph, the peak is to the left of the before urbanization hydrograph. Okay, so that's the reason, but like what is happening? Okay, both of those are really good answers, yeah. So the shift in time just means that the peak is coming sooner. When you urbanize an area, the water moves over the surface more quickly. And so it's getting to some point of interest, whether it's a drain, whether it's a culvert, whether it's a location on a river. The time delay from when it rains to when you see the peak is shorter. So we could look at the time here. It was raining during these time periods, and so we have to wait some amount of time before we see the peak. The peak comes faster after an area has been urbanized because, as it's been pointed out, the surface is more smooth, so water can flow over the face of concrete a lot faster than it can flow over forest litter. You know, broken twigs and leaves and an irregular ground surface, the water moves kind of slowly over that kind of a surface compared to a smooth graded asphalt, concrete, or even just a bare earth that's been graded. And so the water arrives sooner. And those two things are interrelated. The fact that it's arriving sooner is part of the reason why the peak is higher. There's less routing, as it's called. We'll talk a lot more about routing later in the semester, but this is one of the key ideas of the whole semester that I'll come back to again and again. The effects of urbanization and how, as hydrologists, what we need to do is mitigate the effects of urbanization and account for them in our calculations. So here are some of the best management practices, as they're called. When you build a road, put in a new building, there have to be some accommodations made for the disturbance to the hydrology that's been caused. Otherwise, there's going to be more flooding. And part of the reason why there's so much flooding these days is that people just, in the past, didn't have to do anything about the extra stormwater that they were sending down the stream. Anybody seen Amazon, you know, like the big call center that they have by the freeway? So before that was there, it was just a hillside. But they paved that enormous area. They put a big warehouse-type building on there. And now all of the water that used to infiltrate down into the soil, or, at the very least, move slowly over the surface, that water is arriving at the downstream outlets a lot faster than it used to be. And so nowadays there's a philosophy that when you cause that kind of a disturbance, that you should be responsible for mitigating the expense or the damage of the extra runoff that's being sent downstream. And so here in the city limits of Huntington, for instance, newer businesses that are going in have to put in stormwater detention underneath the buildings. An example, the new indoor practice facility that the football team has here on 3rd Avenue, they have a big series of cisterns underneath the parking lot to kind of absorb the first inch of rainfall and delay it and meter it into the storm drains at a more slow rate than it naturally would get in there if there wasn't any kind of storage. Cookout is a newer business, and you may notice that Cookout kind of has like a porous pavement in their parking lot, and that helps to reduce the peak runoff that enters the roadway adjacent to it. Here's a best management practice that is just let's have a nice grassy area next to a road where the rain can infiltrate more easily down into the soil as compared to if it was a paved shoulder. You know, paved shoulder is nicer for motorists to park on, but it doesn't absorb the water. And another benefit of having a vegetated filter strip is that if there are salts or oil or sometimes there are pollutants like lead and benzene, and you know, there's bad stuff that comes out of automobile exhaust, the grass can kind of biofilter that and take up some of the pollutants before it gets into streams and other places where it concentrates. So we're going to just take a look at some of the best management practices that have been developed over the years for mitigating the effects of urbanization. Another is the idea of, instead of having someone storm drain from their roof going into the city's storm network, disconnect that roof from the storm network. And this is something that in Huntington they've really been pushing people to do, is allow the water to just flow into your yard instead of having it go into the city's storm system that's already so overtaxed. Now, people sometimes don't like that because they're worried about the water getting, into their basement or scouring the foundation. And so here you'll notice there's kind of a hose that they've put in to try and get the water away from the foundation of the building. But a simple disconnection for all the for all the houses along a city road can have a huge effect in how overloaded drain is during a storm event. Sometimes, to try and enhance the infiltration, they'll have amended soil and some specialty plants, and so that instead of just having it go onto the grass where you may have puddling or problems when it rains really hard, they will put in something special. And here in town, anybody know that art supply store and bookstore Lotta's? It's on, I think, 4th. Next time you walk by there, notice that in the median strip they have something like this. They have a strip of land where they've amended the soil to improve and enhance infiltration. They've got some plants that take up a lot of water and will respirate it into the atmosphere. So they got a grant, some state money to put that in there, because try and help mitigate some of the flooding they've experienced over the years. Bioretention is just simply the idea that anywhere you can incorporate natural vegetation, do it. It's going to be better than if it was paved. And so on two sides of a parking lot, instead of having it paved, if you put in plants and then slope the parking lot towards that area, then you're going to get all sorts of benefits that help to reduce the peak flows that are seen downstream. Here are some pavers, as they're called, and an impervious surface as a substitute for ordinary asphalt. And porous concrete is a natural extension of that idea, that you don't have to have a surface be impervious to water to be parkable. And here is some porous concrete at the University of New Hampshire, where they're dumping water in there, and you can notice it just keeps absorbing it. Ordinary concrete, the water would be running off. But in this case, what they've done is they've removed the sand from the concrete mix. And so it's cement and it's pea gravel, but there are voids there that are interconnected where the water can actually travel through the concrete and down into the gravel subsurface that they've got underneath it. So it's not a complicated recipe. The only challenge is in the areas that have the freeze-thaw cycle. If this porous concrete isn't well drained, then it's really vulnerable to damage, because if water is in there and it freezes, it's going to expand and then break apart the chunks of the pea gravel that are connected to each other. So it's really critical to have a good drainage system underneath porous concrete, and it looks like here they do. It's not expensive. I mean, it's the same ingredients as ordinary concrete. It's sand. It's gravel and just ordinary cement without the sand. But the added expense comes from the expertise and the attention that has to be placed underneath that layer of concrete. And so it would maybe be 4 or 5 inches of this porous concrete, but then underneath you'd have maybe a foot or 18 inches of crushed limestone that's graded really well so that the water doesn't back up into the porous concrete itself. All right. Ditches or a swale, if they are lined with vegetation, what that does is it increases the roughness and it slows down the movement of water. Now, it also reduces the capacity of the channel to convey, because the velocity is going to be lower and the depths will increase. But anything we can do to slow down the movement of water and delay it inside of the watershed is going to reduce the peak that has to be accommodated downstream. And so when water moves quickly and it all pools to a single place at a single time, that's when damage occurs. But if we can just delay it at every step along the path, then that's going to decrease the height of the runoff hydrograph. Here's an illustration of measures that can be taken to increase infiltration. Here they have kind of like a gravel bed at the center of a pond. And the purpose of this gravel is just that the larger voids helps to receive the water more quickly than if it was small, fine sediments that don't allow for the movement of water quite as fast. Here's a channel where what they've done is put a bunch of little pools along the way. And this is the vertical component of this is exaggerated to make a point that if this was water flowing over a concrete surface, it would move very quickly. But instead, what has to happen when it starts to have water coming off of a road is that each one of these pools has to fill before it then cascades down to the next pool in the chain. And so this is kind of like a series of tanks that fills up. And because of that, there's a lot more delay and routing, and there's some storage volume here. If you just had water flowing over a smooth surface, there would be very limited storage. It would maybe be just a couple of millimeters of depth, and it would be moving very quickly. And so here, not only are we having a delay in time, but also some place for the water to be detained as it makes its way towards a creek, which is the ultimate receiving location for the runoff. Rainwater harvesting is another component of what they've got over at Latas. There's a big barrel behind the building where during the summer they use that water to irrigate the hanging plants here in Huntington. The city goes there to try and make some positive use of the water that's coming off of the roof. Here in the engineering building, we've got a vegetated roof. I'm sure everybody's probably seen it up on the third floor. You can look over and see that. The benefit of having a vegetated roof is that, number one, you're providing some green space into a city that otherwise is just kind of like a concrete jungle, and it doesn't trap as much heat as an ordinary asphalt roof would. But then also these plants can evaporate water and get it back up into the atmosphere. These are a lot of expense and a lot of maintenance, though, relative to the benefit that they provide. There's generally lower hanging fruit available for reducing peak runoff than creating a green roof. The green roof only makes sense if there's going to be some added benefits of people going out there and enjoying it and the beautification aspects. But from just the strict standpoint of the volume of water that's detained and the expense of reinforcing a roof to carry that added load, it doesn't really make a lot of engineering sense unless you have some of those qualitative benefits added in as well. Why do you suppose in this photo it's important to have separate drainage coming off of this business instead of just allowing the water to go into the roadway? First,
it's a gas station.
Yeah, it's a gas station. Yeah, and so, it's very common for people to spill a little bit of fuel each time that they're gassing up, or, as cars are parked there, some oil might drip down onto the ground. And so having a separate pre-treatment area for locations where you know that you're going to have some contaminants improves the quality of the water downstream, and then it can support wetlands, it can support aquatic life more easily if a few hot spots through the city have just a small pre-treatment system where you're kind of, what you might do is collect the water from the surface runoff from this filling station and then have it go to an open grassy pond area, and then the organic pollutants could evaporate, any kind of sediment could settle, and then any leftover water that didn't evaporate could be channeled somewhere else after it kind of been pre-filtered a little bit. Constructed wetlands are really nice, and they're being used a lot more often in suburb areas just because visually they're appealing and it makes people feel like they're back to nature or something. But there can be like some improvements in the chemical quality of water because bacteria that naturally will grow in the water can remove some of the biological contaminants that may come from the runoff, and even the chemical pollutants can be taken up by plants like cattails, and so you're kind of improving the water quality, and the water level may fluctuate in that pond and allow you to have some delay before the water has to go elsewhere into a stream. Now, we're going to talk about a couple of different ponds today, and it's going to be important for you to distinguish between detention and retention. And so this is saying this is a detention pond. And a detention pond is one that is just holding on to the water temporarily, whereas a retention pond either means it's keeping water permanently or for a much longer period of time. So a wet pond or a retention pond is going to have different, like the hydraulic design of them. The elevation at which the water is withdrawn from a wet pond is different from a dry pond, because in a dry pond we want it eventually to drain out again so that there isn't the breeding of mosquitoes, or so that there isn't like a drowning risk or something. You'll notice that this is pretty close to an office building, this detention pond, but in the case of a wet pond, you have to be a little bit more cautious about where they go. And so, for instance, if there were children living in these homes, then the adults are going to have to be conscious of the fact that you've got standing water there and that it could be a drowning risk. And a lot of commercial enterprises are pretty paranoid about being sued, and so they'll have big fences up around their ponds. And in the development that's out by Target, what's that? Is it called Merritt's Creek development? You know where, everybody knows where Target is, right? Next time you go over to Target, look on the left side of the road as you're going up the hill, and they've got a big detention pond there, and it's fenced off because I think it gets pretty deep. Okay, so the general idea here is we want to make the tall hydrograph look more like the short hydrograph. You know, before humans developed land, we had a slow hydrograph with a low peak. And so we want to take measures that are going to transform the after urbanization hydrograph to make it more like conditions were before the disturbance occurred. And so we can do that with stormwater ponds. They're one of the most frequently used tools in response to urbanization. And so we're going to try and mitigate the effects. We want to reduce the volume of runoff because urbanization increased it. And we're going to want to lower the peak flow rates because urbanization increased them. And then wherever possible, try and remove some of the pollutants that accumulated. There is some terminology here that's important for you to know. And as much as it's possible, it's better to prevent runoff rather than to deal with it somehow. Prevent the problem rather than to try and solve the problem. And so source control are measures that are taken. Sometimes they're policy measures, sometimes they're physical things that we can do, but they're thought of as things that are closer to where the stormwater is actually being generated. So you're trying to limit how much water gets into a pipe or into a ditch, trying to solve the problem as early as possible, whereas downstream control are sometimes these very large physical infrastructure things that have to be built because the water is coming and it has to be accommodated before it goes into a stream. And so that could be inline detention, like in Japan, those big caverns that they have, a series of pipes and pumps that are taking the water towards a receiving body. That's an example of inline detention. They also have a pretty sophisticated inline detention system in the city of Chicago. Offline detention could be a pond that is, the water is pumped into the pond or diverted there temporarily. And here in Huntington, we have some stormwater detentions at the treatment plant. At the wastewater treatment plant, there's a big flow equalization basin so that when there's a surge of water going to the treatment plant, we don't just wash out the things that are there and can just temporarily hold on to it and more gradually release it into treatment. So here's a cross-sectional view of an extended detention basin, and here we don't intend it to always be full. The pond is just going to be temporarily full during the peak times of the storm, and the things that you have to note here in this extended detention basin is where the perforations are in the riser pipe. The water comes out of the basin through this riser pipe, and through the perforations being down at the bottom of the pond, that means that water is going to start getting into the outlet as soon as the water comes into the pond. Now, if the water levels are going higher and higher and higher because the inflow into the pond is bigger than the outflow, eventually there's a spillway. This primary spillway is just that once the water gets up to this maximum storage level, it starts pouring into the pipe a lot more quickly than it can get through the pipe through the series of small holes in the perforations. And then even if it goes higher than that, if it overwhelms the capacity of the primary spillway, then there's an emergency spillway. Anybody want to guess what's the purpose of these baffles? Exactly right, to keep debris from blocking the spillway, and they can also separate oil from getting into the primary spillway. All right, so the extended detention basin, key thing here is that the perforations are low. These are most efficient for relatively small and short detention times. Otherwise, they just take up a lot of land. So we have to be conscious of the fact that it's good to detain stormwater, but real estate is expensive. They can settle particulates through the process of sedimentation. That sedimentation that occurs, though, requires maintenance, because if we don't remove the sediments after each storm, then the pond will get filled up. And they also have the risk of mosquito breeding because it's just wet temporarily, and it doesn't usually give a chance for fish that would be consuming the mosquitoes. Like, there isn't an equilibrium of the ecosystem. It's just a wet area where the mosquitoes can set up real quickly, lay eggs, and the predators for mosquito aren't there in the same way that they would be for a retention pond. So here in a retention pond, where it's going to be wet all of the time, you have a more complete ecosystem. Now, from the physical standpoint, look at where the perforations are in this pond. In the detention pond, the perforations were at the bottom because we didn't want it to ever accumulate water. But here, the perforations are towards the top. And where they put the perforations determines the typical level of the water. You know, as the water levels go up during a wet weather event, the water line approaches the spillway, but the main idea is that the perforations are elevated to introduce this permanent pool, and a marsh and other aquatic life can set up on a more permanent basis. And so there's better pollutant removal because of that. Not only is there settling, but also biochemical removal of priority organic pollutants. If the ponds are really deep, though, there can be anoxic conditions. And what we mean by that is that when organic things like leaves get into this pond, or if there's algae that dies and settles to the bottom, there's going to be a layer of scum at the bottom of the pond. And if you've ever swam in a pond before, when you touch the bottom, it's like this really nasty black muck. Has anybody done that before? Yeah, and you maybe get like leeches and worms. And my parents have a pond, and you do not want to touch the bottom of that pond because it's disgusting. The anoxic condition simply means that at the bottom of the pond is going to be a layer of organic material that demands oxygen to break down. It has an oxygen-demanding load, and you're probably learning about this in environmental engineering, or you will soon if you haven't already, that organic material in water, the bugs that consume that organic material also consume oxygen, and so if you run out of all of the oxygen, then different bugs start breaking down the organic material, and the bugs that can do it in the absence of oxygen will give off nasty gases like methane and hydrogen sulfide, and so it can be a really awful smell during anoxic conditions. So there's a risk if it's super deep and the wind doesn't churn that up and stir it, then you can have anoxic conditions. And so the way to prevent anoxic conditions in a permanent pond like this is just to make sure that the pond isn't shielded from wind and that it's not too deep. Or regular cleanouts to try and get rid of all that organic material. All right, so sizing is what we need to talk about for the rest of our class today. And the pond should be big enough to accommodate the difference between the inflow hydrograph and the outflow hydrograph. And so here's the concept. You can see V sub S, that's the storage volume. We have to store the difference between what comes in and what comes out. And I mean, that should make sense, the idea that accumulation is the difference between in and out. So you think of a pond as essentially a box where you've got flow coming in, flow going out, and so the water levels are going to be rising and falling according to the difference between in and out. Now ideally what we'll have is a hydrograph with lots of temporal resolution, lots of really fine time measurements of what's the flow rate in 5 minutes, in 10 minutes, in 15 minutes. More commonly we have a coarser data set where the time measurements aren't as often, and we'll look at how we can handle that. But we're going to, in time increments, look at the difference between in and out and what that means for the storage volume. So to do that, let's look at this example. And we're going to use Excel to handle this example. If you've got Excel available, that's great. You can start it up. If not, that's okay. Just watch and follow along. Here's a very colorful representation of our pond. We've got water coming into, let's assume it's a rectangular pond. And this is kind of a lame assumption here. We're going to assume that the side walls are vertical. Just because what that does is it makes it easier to calculate the volume in the pond as the water levels rise. Now more commonly you'd have sort of like a trapezoidal section in a pond, and so as it gets deeper the cross-sectional area is increasing. But just for sake of simplicity, to show you the structure of these calculations, let's assume that it's a vertical wall. And so we've got an inflow. This is showing over time how much water is coming into the pond. And now the flow out of the pond is going to be governed by the orifice equation. You remember back to fluid mechanics lab, the orifice equation, as the water level gets deeper and deeper, then the flow rate through the outlet pipe is going to be increasing because the pressure forcing water through that outlet pipe is increasing. All right, so let me start up Excel here, and I'll show you the template that you can use to solve problems like this. All right, so we need to have some pond width that we're going to be working with, and in this example, the width and the length of the pond is 65 meters. Okay, so pond width 65, pond length is 65 meters. And we're going to use those to calculate the area of the pond. Equals width times length. All right. Let's have the coefficient of discharge for the pipe. That's something that goes back to the orifice equation, and so it relates the amount of energy loss as the water approaches that opening in the pond and flows through it. So 0.59 is what we'll use as a typical orifice equation, C sub D. And then the pipe diameter in meters. Here in this little illustration we're assuming, let's see what happens with 0.25 meters as our outlet. And then pipe area, which we're going to calculate based on the diameter. So it's equal to pi times d squared divided by 4. Okay. Now, we're going to have time in hours and then the inflow into the pond in cubic meters per second. All right, I'm just going to copy and paste. You're going to have to type it because you can't copy and paste off the screen like I can. Okay, so here is the time and the water that's coming into the pond. Okay, our next column is going to be where we calculate the volume that comes in during a time increment. And it's going to be cubic meters. Let me wrap here. So what we're saying is that from time 0 to time 1, we're assuming that the inflow rate is 0. So there's not going to be any volume that comes in during that time. But during the 1 o'clock hour, we're going to have 3,600 seconds of this flow rate. So I'm going to say the flow rate times the number of seconds per hour, and that tells me the volume of water that came in during that time period. And now I can just drag this down since I've got the formula for each of it. So we're turning the inflow flow rate to an inflow volume. All right. The next column I'm going to put in here is the accumulated volume, also in cubic meters. And during the first hour, there's no flow rate in, so there's not going to be any accumulation. But for the other hours, I'm going to have to look at the difference between the in and the out. So I'm going to leave the rest of this blank for now. I'm not going to fill it quite yet. We need to have a column that is pond depth, because remember, the flow rate out depends on how high the water level is. As the water level rises, then that's going to increase the flow rate out. Now, pond depth is one thing, but you'll remember from the orifice equation that it's actually h that goes into the orifice equation, where h is the distance from the water level to the center of the pipe. So here, h is going to be the pond depth minus half of the pipe diameter. Because, let me just do a little sketch on the board here. If we've got, here's the bottom of our pond, okay, and here's the water level, and here's the pipe coming out. Let's say, for instance, that we had 2 meters of water in the pond, but now we've got a 0.5 meter pipe diameter. What that would mean is that h goes from the water surface down to the center line of the pipe. So h in this case would be 2.0 minus 0.5 divided by 2, so it would be 1.75 meters. So just as a refresher, we need to distinguish between the depth of the water in the pond and the depth of the center line. I'm going to leave that formula in for now, but I'm going to override that to 0 because there's essentially no water in the pond yet, so h should be 0. So I'll come back to that in just a moment. Now there's the outflow from the pond, which is also going to be cubic meters per second. And then our final column that we have to create is the volume out during the time increment. And that's a cubic meters. All right, so it'll make more sense when we step through some of the calculations here. So during the first hour, there's no flow rate, so there's no volume in, there's no pond depth, there's no outflow, there's no volume out. It's just everything is 0 during the first time increment because there's no inflow. Now, since there was no outflow, then the accumulated volume is simply going to be the volume that came in during the time increment. So if that's our volume that's in there, now the depth is going to be the volume divided by the pond area. I'm going to anchor my reference to the pond area. So at this time, we've got a certain pond depth, and now the H I didn't anchor my reference to C sub D like I needed to, or to the pipe diameter. So let me anchor that reference to the pipe diameter, drag that down. All right. So the H is just the distance from the water surface to the center of the pipe. Now the outflow is going to be the square root of 2GH. So C sub D, anchor that, times the square root of 2 times G, which is 9.81, times H. And that is telling me how quickly the water is flowing out from the pond. All right, and then the volume out during this time increment is just going to be the flow rate times 3,600. So now, this is where it gets a little tricky. All right, the accumulated volume for the next time is going to be how much water was in there during the previous time increment, plus the new that came in during this increment, minus the water that flowed out in the previous hour. Now this is like kind of one of the limitations of numerical integration, is that, you know, here I'm doing it in hour by hour steps. It would be better if I had this data in 5-minute steps, because what we're essentially saying is that the outflow from the previous hour is what we're applying to conditions during this hour. But we're forced to do that. We have no other choice. But just to remind you what that means is that the accumulated volume at any given time is going to be how much water was there during the previous hour, what came in, and what went out. So in this case, we can see that there's a lot of water flowing out during this time increment. The outflow from the pond is very quick. Hold on a second. Square root of 2GH. This is just the velocity so far. I didn't yet multiply that by the area. So remember, Q equals VA. And so Q is going to be area times C sub D times the square root of 2GH. Okay, so I need to multiply here. My outflow right now doesn't have the pipe area factored in yet. Okay. That's more sensible. So we've got the volume in, the volume out, and then here's the key thing, is that for my next hour it's going to be the volume in plus the previous volume minus the volume out from the previous hour step. And so now I can drag this down, and it will simply calculate based on the updated values. I can drag all of these down and see what's happening with the pond. So in the case of this pond, it's draining very slowly. You know, it is draining, but the accumulated volume, the depth is decreasing relatively slowly. If I wanted it to drain within 10 hours, then I could make the pipe diameter a little larger. What if I made it 0.35? And what you can see is that the depth is decreasing more quickly, and we could extend this to be, you know, more time intervals and just see over time what's happening with the pond. already giving me some flow rates. All right, so in this case, it looks like when it says this number thing, it means that the pond is empty. So if we had a pipe diameter of 0.35, then it's going to take until 3 p.m. to be all the way drained. If I changed it to 0.3, then the water stays in the pond longer. Now it's taking until 7 o'clock. All right, so that's part of the homework assignment that you're going to have to do. And I apologize we didn't have a chance to work some examples that was related to the AASHTO storage volume and the apt and grig. But these are just basically plug and chug type equations. And so I'd like you to still attempt that for the homework assignment. I'll post my example calculations online and I'll send an email to you. I had this example that was comparing these two methods, but they're relatively simple. We're just, in these other methods, we're estimating the volume of a pond required by assuming a triangular peak flow. So I don't want to keep you any later than I already have. We're 2 minutes over time there, but let's take a look at these announcements. So on Tuesday, your homework assignment is due. I'm going to upload to MU Online not only the apt and grig and AASHTO example that we didn't get through. I'm going to give you an idea. This is how big the example is. It's pretty quick. I'll upload that, and then I'll also post a PDF copy of this spreadsheet so that you can, if you didn't work the example in class today, you can work the example and make sure that your numbers work out. I won't post an Excel because then you can just plug the homework straight into the Excel, but I will give you a PDF of it. All right, that's it for today. Feel free to take another sausage if you need some electrolyte replacement, and I will see you on Tuesday.